We'll get started. So, the Chapter 7 homework is due on the 27th. The Chapter 7 quiz will also be on the 27th. Names? And on the 27th, we will be doing a review of chapters 5, 6, and 7. The exam on chapters 5, 6, and 7 is on the 29th. The labs today and on the 27th are for makeups. Also, I will be available Monday, Tuesdays, and Wednesdays from around 10 to 1 p.m. and Thursdays from around 11:30 a.m. to 1 p.m. Name? So, today we're continuing on with the subject you voted for, which was nuclear physics. So nuclear physics is the study of the nucleus, this inner part of the atom. And the characteristics of the atomic nucleus are very important to our modern society because we use various nuclear reactions for a variety of purposes. You use them for the diagnosis and treatment of cancer and other diseases, geological and archaeological dating, chemical analysis, nuclear energy and nuclear disposal, the formation of new elements, and the radiation of solar energy is generated by a nuclear reaction. So, pretty much everything is dependent on nuclear reactions. And finally, the generation of electricity. So, some early thoughts on the elements, the idea of elements. The Greek philosophers from around 600 to 200 BCE were among the first people to speculate about the basic substances of matter. And there were several different ideas about this. And the most influential of the Greek philosophers for science was Aristotle, and he speculated that all matter on Earth is composed of only 4 elements: earth, air, fire, and water. He was wrong on all counts. But the idea of the matter being made of small indivisible particles called atoms was something that was around with the Greek philosophers as well. Things like that. That's where the term comes from. So, a lot of the elements got their symbol. The Swedish chemist Jan Jacobs Berzelius used 1 or 2 letters of the Latin name to designate each element. So this is why a whole bunch of the elements have very strange seeming symbols. So copper is Cu because the Latin name is cuprium. Gold is Au because the Latin name is aureum. Iron is Fe because the Latin name is ferrium. Lead is Pb because the Latin name is plumbum. Mercury is Hg because the Latin name is hydrargyrum. Potassium is K because the Latin name is kalium. So a lot of the funny elemental symbols come from the Latin names. And if you speak a Romance language, like Spanish or French, or one of the various languages descended from Latin, it's quite possible the names of the elements are more similar to the Latin names, and these will make more sense. Now, since Berzelius's time, we've moved on from Latin as the primary language of science. And so at this point, most elements have been symbolized by the first 1 or 2 letters of the English name. You're not going to be tested on this, so you're not expected to know them, but these are 35 useful elements to know. Aluminum is Al, argon is Ar, barium is Ba, boron is B, bromine is Br, calcium is Ca, carbon is C, chlorine is Cl, chromium is Cr, cobalt is Co, copper is Cu, fluorine is F, gold is Au, helium is He, hydrogen is H, iodine is I, iron is Fe, lead is Pb, magnesium is Mg, mercury is Hg, neon is Ne, nickel is Ni, nitrogen is N, oxygen is O, phosphorus is P, platinum is Pt, potassium is K, radium is Ra, silicon is Si, silver is Ag, from argentum, which is the Latin for silver. Sodium is Na, I can't remember where that's from. Sulfur is S, tin is Sn, uranium is U, zinc is Zn. Now, all matter that you encounter on a regular basis is composed of atoms. An atom is made of 3 subatomic particles. Around the outside part of an atom, there are electrons, and in the nucleus, in the center, there are protons and neutrons. Electrons have a negative charge, and all electrical effects that you encounter involve the movement of electrons. They're the light, easy to move around, negatively charged particle. Protons have a positive charge, are in the nucleus. Because the protons are positively charged and the electrons are negatively charged, the electrons are attracted to the protons and thus orbit around the nucleus. And so the nucleus of the atom contains the protons and neutrons, also called nucleons. The electrons surround or orbit the nucleus, and the electrons and protons have equal but opposite charges. But they're very different in size. A proton is about 2,000 times more massive than an electron. And then the nucleus, which is full of positively charged things, which would naturally want to like tear itself apart, is held together by the strong nuclear force. So the major constituents of an atom are the electron, which has an electronic charge of -1 of quantum charge, which is minus 1.6 times 10 to the minus 19 coulombs. It has a mass of 9 times 10 to the minus 31 kilograms. The proton has a +1 quanta of charge. The electronic charge, this 1.6 times 10 to the minus 19 is often written as a lowercase e. So plus 1.6 times 10 to the minus 19 coulombs. And it has a mass of 1.67 times 10 to the 23rd. So you can see that, sorry, 10 to the minus 27. So the proton is about 2,000 times the mass of the electron. And a neutron has a charge of 0. And its mass is basically the same as a proton, 1.675 times 10 to the minus 27. So it's a little bit more massive than a proton. So protons and neutrons have nearly the same mass. They're about 2,000 times more massive than the electron. The electron was discovered by J.J. Thomson in 1987. The proton by Ernest Rutherford in 1918. And the neutron by James Chadwick in 1932. And even though they're the bits that move around, they have a negative charge, and I believe that's Ben Franklin's fault. Because he needed to choose which side was positive and which side was negative, and he made an arbitrary choice, and it was unfortunately the one that's awkward. So Rutherford discovered the nucleus. So J.J. Thomson had proposed this idea. He discovered the electron, and he proposed this idea that the electrons were embedded in sort of this model of the atom called the plum pudding model, where there was sort of a continuous positively charged mass with the electrons dotted throughout it, which predicted that if we shot alpha particles, which had been discovered by this point, there's something that's generated by radiation. They're actually helium nuclei, but people didn't know that at the time. If we shot alpha particles at a very thin piece of gold foil, you would expect them to go through. And when Ernest Rutherford did this alpha particle scattering experiment, an alpha particle is a helium nucleus, and he shot these heavy alpha particles at this incredibly thin, few atom thick sheet of gold foil, he was shocked to discover that some of them bounced. And I believe the analogy is that it would be like shooting bullets at tissue paper and seeing some of them bouncing. And this was how the nucleus of the atom was discovered. They discovered that all the positive charge was actually concentrated in a very small area in the center. And this deflects the positively charged alpha particles. So only about 1 out of 20,000 alpha particles bounce back, and Rutherford could only explain this by assuming that each gold atom has its positive charge concentrated into a very small nucleus. The diameter of the nucleus is about 10 to the minus 14 meters, while the diameter of the electron orbits is about 10 to the minus 10 meters. So the nucleus is about 1/10,000th of the size of the whole atom. And the atomic mass is concentrated in the nucleus. About 99.97% of the mass is in the nucleus. Because the electrons are so much lighter than the protons and neutrons. So almost all the mass of an atom is concentrated in the nucleus. So the volume or size of an atom is determined by the orbiting electrons, which is about 10,000 times the diameter of the nucleus. And if you were able to pack only nuclear material into a sphere the size of a ping pong ball, it would weigh 2.5 billion tons. And amusingly enough, there are some places in the universe where material that dense exists, called neutron star. But you need enormous gravity to pull it off. Because if you were able to pack only protons and neutrons into a sphere the size of a neutron ping pong ball, it would weigh 2.5 million tons, and then it would explode because nothing would be holding it together. So this is a visual representation of a nucleus. It's made of tightly packed protons and neutrons. They're being held together by the strong nuclear force, but the strong nuclear force only works over a certain range. And so eventually it weakens. And so as you get to bigger and bigger atoms, you need more and more neutrons to hold it together. And actually all atoms above a certain mass, a certain number of protons, are unstable. So when we describe an atom, we can do this with a couple of numbers. There is a few numbers. The first of these is the atomic number. The atomic number is the number of protons in the nucleus of an atom. This is what determines what element we're talking about. So you can represent the atomic number with a number, but it's also what's represented by the symbol of the element. So if it's carbon, the atomic number is 6. If it's oxygen, the atomic number is 8. If it's helium, the atomic number is 2. So the number of protons defines the element, and that's the atomic number. It's also called C. It also delegates the number of electrons you'd normally have in the atom. It's possible, though, for an atom to gain or lose electrons, then it becomes an ion. So if an element gains or loses electrons, the resulting particle is called an ion, and it either has a positive or negative charge. For example, if a sodium atom loses an electron, it becomes a sodium ion, Na+. And you are full of sodium ions. You use them to make all kinds of things in your body work, like your nerves require sodium ions. Sodium actually will very happily lose an electron. So how you form table salt, for example, is the sodium gives up its electron to a chlorine, and then they're electrostatically attracted to each other. So if you want to describe an atom, the other number is the mass number, A. And this is the sum of the number of protons and the number of neutrons. And an isotope of a particular element is a particular variation of that element with a certain number of neutrons. So, for example, hydrogen, the simplest element, has 3 isotopes. There's just regular hydrogen, which has an atomic number of 1 and an atomic mass of 1, just a proton. Then there's deuterium, which is also known as hydrogen 2. That has an atomic number of 1 and an atomic mass of 2. It's 1 proton and 1 neutron. And lastly, there is tritium, which has an atomic number of 3, an atomic mass of 3 and an atomic number of 1. It is 1 proton and 2 neutrons, and it's radioactive. And it's used to make glowing things, various stuff sometimes. But yeah, the isotope is when the number of neutrons vary in the nucleus of a given element. The number of protons will always be the same. There are only 118 known chemical elements, but there's about 3,000 isotopes. No. And so every element has multiple isotopes, pretty much. So some elements have several isotopes, like carbon. The most common form of carbon is carbon-12. There is also about 1% of the carbon out there is carbon-13. And then an even smaller portion is carbon-14, which is radioactive and decays. And actually carbon-14 is what we use for radiocarbon dating. So isotopes of a single element will have the same chemical properties. They have the same number of electrons. They do chemistry the same. Or more or less the same. The only thing that varies is their mass. This could have a slight difference in chemistry for some of the lighter elements where there's a bigger change in mass. So like deuterium chemistry is a little bit different from hydrogen chemistry, but it's a tiny difference. Due to the various isotopes, they will behave slightly differently during reactions, but otherwise, their chemical bonds that they can form and all that are the same. So here, for example, are the 3 naturally occurring the naturally occurring isotopes of hydrogen. There are hydrogen 1, hydrogen 2, and hydrogen 3, or protium, deuterium, and tritium, for the fancier names. And in naturally occurring, 1 hydrogen atom in 6,000 is deuterium. And that's not really going to change because deuterium is stable. And then 1 in 10 million is tritium. And the reason tritium is so much rarer than deuterium is because, at least partially because tritium is unstable. It decays over time. And you can have heavy water. You may have heard of heavy water. Heavy water is G2O. it's water with the hydrogens replaced with deuterium. Both the hydrogens are deuterium. Heavy water can be useful for various things, which is why we have a bottle of it in the big lab over there for use with the NMR. So let's look at this atom of fluorine 19. The atomic number is 9. So there are 9 protons and 9 electrons. The mass number is 19. To find the number of neutrons, we subtract the atomic number from the mass number, and we get that there are 10 neutrons. So fluorine 19 has 9 protons and 10 neutrons. So protons and nucleons are in the nucleus. Electrons orbit around the nucleus. The atomic mass number is the number of protons plus the number of neutrons. The atomic number is just the number of protons. The neutron number is the number of neutrons. But usually things will be expressed with their atomic mass and their atomic number. And an isotope is an element with a different number of neutrons and the same number of protons. And sometimes their physical properties are a little bit different. So that was actually relevant to my PhD research because I was studying solid helium. And under the conditions I was working at, we were studying as you change the amount of helium-3 in your helium mix, how that affected the phenomena we were looking at. Because helium-3 has different, under the conditions I was working at, helium-3 has significantly different properties than helium-4 because its spin is different. So it's a fermion and not a boson. It forms superfluids differently, which is the relevant thing I was working on. So if you look at periodic table, like the one on the wall over there, there will be an atomic mass listed. That is the average atomic mass for naturally occurring material. It will not be a full number. It's a weighted average mass for an element in a naturally occurring sample. So for example, chlorine, chlorine is, the atomic mass is 35.453. That's because chlorine consists of 2 isotopes. One about 3 times as common as the other. One is 35, has a mass of 35, and the other has a mass of 37. And so the average mass is what goes on the periodic table. The atomic mass is measured in atomic mass units, which is basically the weight of a proton or a neutron. It's calibrated so carbon-12 has an atomic mass of exactly 12 atomic mass units. That's how it's defined. So carbon-12 is the standard. And the weighted mass of all carbon is slightly higher. It's 12.011 because there's a small amount of carbon-13 and a small amount of carbon-14. About 1% carbon-13 and less than that carbon-14. So we've talked about some forces of nature, gravitational and electromagnetic. The nucleus is where the other 2 fundamental forces of nature occur. So the nucleus is not being held together by gravity. Inside an atom, gravity is negligible. So the electromagnetic force between a proton and an electron is 10 to the 39 times greater than the gravitational force between them. They're very light and they're charged. The electromagnetic forces are the only important forces on electrons and are responsible for the structures of atoms, molecules, and all matter in general. All of chemistry is electromagnetic forces, basically. But the nucleus of an atom is very small and packed with neutrons. Okay, that's not a problem, and protons that are all positively charged. So the nucleus of an atom wants to explode. Like, it does not want to be packed into a tiny ball. Because all the positive charges are repelling each other. So something has to exist to hold it together. The repulsive forces of the nucleus are huge, and the nucleus should fly apart. So there must be at least one extra fundamental force that holds the nucleus together. Can't be gravity, because gravity is pathetic. This is what's known as the strong force, or the strong nuclear force. It is called that because it is strong. It's attractive at distances less than about 10 to the minus 14 meters. Larger than that, it gets weak. It goes away. It's complicated. We're not going to go into any details about how the strong force works, because, yeah. I didn't take that class in grad school. So, for a large nucleus, the forces are very complicated. But what it boils down to is that an individual proton is only attracted by the 6 or 7 closest nucleons to it. But it's repelled by all the other protons. This is why, as you go up in the periodic table, at the beginning of the periodic table, you generally have an even number of protons and neutrons. But as you get higher in the periodic table, to be stable, you need more and more neutrons. And in fact, when the number of protons exceeds 83, the electrical repulsion will overcome the nuclear force, and the nucleus is unstable. Now, there's plenty of natural. Unstable just means under the right conditions, it will decay. Doesn't mean it happens fast. So there's plenty of naturally occurring elements that are unstable. So spontaneous disintegration or decay will occur to adjust for the neutron-proton imbalance. It may not happen very fast. So, like, we're talking things can last for billions and billions of years, but they are technically unstable. There's also a weak nuclear force in the atom. It's called the weak nuclear force because it's weaker than the strong nuclear force. It's also weaker than the electromagnetic force. It's much stronger than gravity, though, because gravity is pathetic. Gravity is just by far the weakest of the fundamental forces and doesn't fit with the rest of them. So it's a very short-range force. The primary thing the weak nuclear force is involved in is the process known as beta decay. It's involved in the process that allow protons to turn into neutrons and neutrons to turn into protons. And physicists have organized the 3 known atomic forces, electromagnetic, weak, and strong, weak nuclear and strong nuclear, into a single unifying theory. It's called the Standard Model. And one of the big problems with physics at the moment is that we have the Standard Model and quantum field theory, which describes the very small. And we have general relativity, which describes the very big. And they both work very well, but their math do not work together. Like, their maths are. So, we know that there needs to be a better solution, but neither of them has broken yet. So it's hard to figure out what a better solution would be. So in an atom, there's a mass number, which is the number of protons and neutrons. That's the total number of nucleons. When you describe an isotope, which is when the number of neutrons vary, you generally describe it by name of the element followed by the mass. So helium-3, helium-4. There's also helium-5, but nobody does anything with helium-5. Atomic nucleus, Z is the number of protons. That's the atomic number. The mass number is the number of protons and neutrons. And the way you write it, you write the mass number is a superscript before the chemical symbol. And if you want, you can write the atomic number as a subscript in front of the chemical symbol. That's not very common. Because the chemical symbol tells you what that is. These are giving you the same information in two different ways. Now, radioactivity or radioactive decay is the spontaneous process of a nucleus changing. It's undergoing a change by either emitting particles or rays. And there are three things that commonly come out of radioactive decay. And they're named after the first three letters of the Greek alphabet. Because sometimes people aren't creative. They are alpha particles, beta particles, and gamma rays. So, a nucleotide is a specific type of nucleus, like uranium-238 or carbon-14. And a radionucleotides are specific isotopes that undergo radioactive decay. The radioactive isotopes or radioisotopes, they're nucleotides whose nuclei will undergo spontaneous disintegration. And substances that give off such radiation are said to be radioactive. So when we talk about radioactive decay, there is a parent nucleus, what you started with, a daughter nucleus or a daughter product, what you end up with after the decay. And there's three common ways that a nucleus can decay. They are alpha decay, beta decay, and gamma decay. Alpha decay involves the emission of an alpha particle. This is a helium nucleus, 2 protons and 2 neutrons. Nucleus is unstable, it spits off a lump of itself. Beta decay involves a proton turning into a neutron or a neutron turning into a proton. There's 2 versions of beta decay. And the emission of either an electron or the emission of a beta particle. A beta particle is either an electron or an anti-electron, depending on which way that transformation went. There's also a neutrino emitted, or an anti-neutrino, again, depending on which way it went. If it's an electron, it's an anti-neutrino. If it's a positron, it's not an anti-neutrino. If I remember correctly. And then gamma decay involves the emission of a gamma ray. That is, the nucleus is energized, over-energized, and unstable, and it spits out some light to settle down. So alpha decay is the disintegration of a nucleus into a nucleus of another element with the emission of an alpha particle. So the atomic mass will go down by by 4, and the atomic number will go down by 2, because it spits out 2 protons and 2 neutrons as an alpha particle. It's a helium nucleus. So you're subtracting 4 from the mass and 2 from the atomic number. Beta decay is where a neutron, the traditional beta decay is where a neutron is transformed into a proton with the emission of a beta particle, which is an electron. There's also the opposite can happen. You could have a proton turned into a neutron and emit an anti-electron. But this does not change the mass, because the number of protons and neutrons doesn't change. But it does increase the atomic number by 1, because it's emitting effectively -1 with the electron. And gamma decay occurs when the nucleus emits a gamma ray, and becomes a less energetic form of the same nucleus. Nucleus doesn't change. It just stops being extremely energetic. And if you have some source of radiation, and put it between a couple of charged plates, alpha particles will go one way because they're positively charged. Beta particles will go the other way because they're negatively charged. And gamma rays will go straight because they have no charge. Same thing if you put them in a magnetic field. It'll get the same effect with the magnetic field, but the field would have to be coming out of the board. Into the board, sorry. There's a sign. So here are some examples of some nuclear decays. Here is thorium-232, which has an atomic mass of 232 and an atomic number of 90, decaying into radium-228, which has an atomic mass of 228 and an atomic number of 88, by emitting a helium nucleus. You can see if you add up the atomic masses, this is 232, 228 plus 4 is 232. And if you add up the atomic numbers, 90 is equal to 88 plus 2. Here's beta decay. Carbon-14 decays into nitrogen-14. You can see the atomic number goes up by 1. The mass stays the same because it's emitting an electron, which has an atomic mass of 0 and an atomic number of -1. And gamma decay, here we have energized 204 lead-204 becomes unenergized unexcited lead-204 plus a gamma ray. So the sums of the mass numbers and the sums of the atomic numbers will be equal on each side. So here, uranium-238 undergoes alpha decay. We can write the equation of the process. We have uranium-238 equals something plus a helium nucleus, which is helium-4 atomic number 2. Uranium is 238. Uranium-238 is atomic mass 238, atomic number 92. So to get the atomic mass, we subtract 4 from this, so we have 234. To get the atomic number, we subtract 2 from 92, we get 90. And so we get that's thorium-234. Yes, thorium. So here are the nuclear radiations. There's alpha particle, which is a helium nucleus. It has a charge of +2 and a mass number of 4. Beta particle has a charge of -1 and a mass number of 0. Gamma ray, charge is 0, mass number is 0. There's a positron, which has a charge of +1 and a mass number of 0. And a neutron, which has a charge of 0 and a mass number of 1. So you can also have beta decay where so we talked about a neutron turning into a proton. You can also have the opposite happen. That emits a positron. So here, for example, is the decay series for lead from uranium-238 to lead-206. So it starts at uranium-238, becomes thorium-234, then I don't remember what that is. I should forget the names. Well, Pa-234, then uranium-234, which then decays to thorium-230, then radium-226. Radium, and then what RM is. I don't remember all that, And then polonium-218, then lead-214, then bismuth-214, then polonium-214, then lead-220, bismuth-210, polonium-210, and then finally lead-206. So you generally get a sequence of beta and alpha decays. Where the alpha decays move it down in mass, and then the beta decays move it up in atomic number. And so you can end up sort of zigzagging down like this. So how do you identify which nuclei are unstable and which ones are stable? Well, we find that an interesting pattern emerges. Most stable nuclei have an even number of both protons and neutrons. So generally nuclei, you want to have even nucleides, so even number of protons, even number of neutrons. And most unstable neutron nucleides have an odd number of both protons and neutrons, odd nucleides. So a nucleide will be radioactive if its atomic number is greater than 83, if the number of neutrons is less than the number of protons, with two exceptions, which is regular old hydrogen, which is just a proton, so it can't really break apart. And then helium-3, which is two protons and a neutron, and it happens to actually be small enough to be stable. Or it's an odd nuclei, with a few exceptions. Deuterium, so hydrogen-2, lithium-6, boron-10, and nitrogen-14. Again, those are all light nuclei. So now those are the odd nuclei in like the first row, and not even all of them. So here we want to identify the radionucleotide in each pair and state our reasoning. So we have lead-208, and well, this is just wrong. This says helium-222 out of 86, but that's not helium. Z is above 83. Neon-19 has fewer neutrons than protons, so it's unstable, while neon-20 is stable. Copper-63 is odd-even, while copper-64 is odd-odd, so it's unstable. So the pairing effect stabilizes. So even, there's 160 stable nucleides. Even-odd, there's only 52 stable nucleides. Odd-even, there's 52 stable nucleides. And odd-odd, there's only 4 stable nucleides. And there's sort of a strip in red here of stability, while the blue dots are known radioisotopes. The red dots is this band of stability. So along this band is where all the stable nuclei are. And you can see it starts close to the 1-to-1 ratio of protons to neutrons, and then it steadily moves further away from it as they get bigger. Now, while many of these radionucleotides are unstable, you might ask, how unstable are they? How do we describe how unstable they are? And that we can do with what's known as the half-life. A half-life is because whether or not one of these nuclei breaks apart is random. But the chances of it happening depend on its nature. So to get a way to measure that sort of process, we could say, how long does it take for half the nuclei in a sample to decay? So how long does it take for half the material there to fall apart? Because any one of them could happen at random. So that is a half-life. A half-life is the time it takes for half the nuclei in a given sample to decay. So if I started out with 32 nuclei, after one half-life, I'd have 16. After two half-lives, I'd have 8. After 3, I'd have 4. And after 5, I'd have 2, and so on. So after one half-life is expired, half the original amount remains undecayed. After two half-lives, you get half of half, which is a quarter remains, and so on. And different nuclei, different isotopes have different half-lives. And they can vary from tiny, tiny fractions of a second to billions or trillions of years. So here's the decay curve for any radionuclei in half-lives. So again, after one half-life, you're going to cut in half, then to a quarter, then to an eighth, and so on. So what fraction in mass of a 40 milligram sample of iodine-131 with a half-life of 8 days will remain in 24 days? So 24 days is 3 times the half-life. That's 3 half-lives. So we start with the given amount, 40 milligrams, and we have it 3 times. So that's going to be an eighth of what we started with. So after one half-life, we'll have 20 milligrams, so that's after 8 days. After 16 days, we'll cut that in half again to 10 milligrams. And then after the full 24 days, we'll be down to 5 milligrams. And this process of decay means that you can use radionuclides like a clock. You can measure the age of things by how much these nuclei have decayed. So here, what fraction of the strontium-90 produced in 1963 with a half-life of 29 years will remain in 2021? Well, that's 58 years. So that's 2 half-lives. So a quarter of the original strontium-90 will remain. So an example of something that we do use to measure half-time is carbon-14. While you are alive, the amount of carbon-14 in your body stays more or less steady. Because carbon-14 is constantly being replenished in the atmosphere by cosmic particles striking nitrogen in the atmosphere. That makes more carbon-14. It enters the carbon cycle. Eventually, it ends up in our food we eat. So anything that's alive has a certain amount of carbon-14. A certain portion of their carbon is carbon-14. Once you die, though, you stop interacting with that system. And so the carbon starts to decay. So you can use this to date things. So how long would it take a sample of carbon-14 to decay to 1/4 of its original activity? The half-life of carbon-14 is 5,730 years. To get down to 1/4 of its original activity, it would need to decay for 2 half-lives. That's 11,460 years. So we can use this to date things. There are a whole bunch of complications in this, but this is actually something is used for dating, and we've gotten better and better at this process over time. So in order to determine the half-life of a particular radionuclide, you have to monitor the activity of a known amount in the laboratory. You look at the emission of decay particles, the rate at which the sample is emitting decay particles, and how it changes over time. When that activity rate has fallen to 1/2, you've reached 1 half-life. Now, If the half-life is very long, what you can do is you can figure out when that would be from measuring a shorter period of time. But this is measured with a Geiger counter or some other detector of those particles. So a Geiger counter is sort of the traditional method for detecting incoming radiation. When a high energy particle from a radioactive source enters the Geiger counter, passes through this window. It ionizes an argon atom, giving off a small pulse of current, which gets counted and amplified into the familiar clicks. Most modern radiation detectors use something different than this. They don't use argon in a Geiger counter. They use a more solid state simulator material, but it's the same idea. When the radiation enters it, it sends off a small electrical pulse. And because of the constant decay rates, radioisotopes can be used as nuclear clocks. We can determine the ages of objects that contain radioisotopes. So under certain circumstances, things like rocks, when they form, will only have certain elements in them. Which means by comparing the parent element to the daughter element that wouldn't normally be there when it forms, we can date these materials. So this is used to date rocks, or radiocarbon dating is used to date biological material. So carbon-14 dating is the dating for archaeology. This is used on materials that were once part of living things, wood, bones, parchment, etc. Because carbon-14 is formed naturally in the upper atmosphere and then gets dispersed into the atmosphere, becomes carbon dioxide, gets absorbed by plants. So all living matter contains about the same level of carbon-14 at an activity level of about 16 counts per minute per gram of total carbon. And so what you can do is once something dies, it starts to decay. There's a whole bunch of things you have to do for actual accurate dating. There's a whole bunch of corrections you have to take into account, because it turns out the amount of carbon-14 in the atmosphere varied over time. And then there are certain things that can cause things to look older than they actually were. You can have people consuming what is effectively old carbon. If you eat a lot of fish, you'll have less carbon-14 in your body, because the fish eat things that were in the water. The carbon in the water cycle stays there, doesn't interact with the atmosphere as much. And you could end up with stuff that's just sort of slightly older, and the dates could be off with it. Now, once an organism dies, it ceases to take in carbon-14, and the carbon-14 present at death will start to undergo radioactive decay. So the longer something has been dead, the lower its radioactivity of each gram of carbon in its remains. Because the other types of carbon, carbon-12, carbon-13, they're stable. Nothing's happening with them. So cosmic rays turn nitrogen-14 into carbon-14. The carbon-14 reacts with oxygen to form carbon dioxide. That ends up in plants for plant respiration. Then living things, people or animals eat the plants, and then you can measure the amount of decay there. So after about 10 half-lives, we might be better than that these days because we've gotten better at carbon dating. But after about 10 half-lives, very little carbon-14 remains. So it's barely measurable. So the limit in radiocarbon dating depends on the ability to measure very low activity in old samples. So the current limit, this is probably a little out of date. So we're probably a bit beyond this now, but it's still roughly 40,000 to 50,000 years. The main advance, I think, has not been so much that we've extended the time period we can measure to back further in time, but we've managed to do it with smaller samples. So for example, if you find an old scroll in a cave that has a carbon-14 activity of 4 counts per minute per gram of total carbon, about how old is the scroll? Well, the plant originally had an activity of around 16 counts per minute. to get to 4 counts per minute, you need 2 half-lives, because you cut it in 4. The half-life of carbon-14 is 5,730 years. So this would imply that the scroll is 11,460 years old. So between around 11,000 and 12,000 years old. This would be problematic. And you would suspect that something went wrong in this. Because that's really old for a scroll. In fact, that's older than a scroll should be. So, we know that radioactive nuclei can spontaneously change into nuclei of other elements. This is a process called transmutation. Scientists wondered if the reverse was possible. Could a particle, a proton, or neutron be added to a nucleus to change it into another element? And the answer to this is yes. And this process is called the nuclear reaction. So that alchemical dream of turning lead into gold is possible. And in fact, has been done. And is not at all cost effective. The estimated cost is something like billions of dollars per gram of gold created. Like, they made atoms. And it costs large amounts of money in particle accelerators. It was more to prove that it can be done, but it's been done maybe a couple of times. So it's possible, but it's not easy. Oh, and the gold is radioactive. So the first nuclear reaction was done in 1919 by Ernest Rutherford, who bombarded nitrogen-14 with alpha particles. And the result was an artificial transmutation of a nitrogen isotope into an oxygen isotope. Alpha particle hits the nitrogen, goes from nitrogen-14 to oxygen-17 plus a proton. So the conservation of mass number and the conservation of atomic number holds in nuclear reactions, just like in nuclear decay. The total mass number on both sides is 18. The total atomic number on both sides is 9. And the general form for a nuclear reaction is a plus big A equals big B plus little b. So the particle that bombards A to form nucleus B and emitted particle B, little b. Generally what happens is you whack a particle into another particle, it changes into something new and spits something out. So, in addition to the particles in the table below, you have alpha particles, beta particles, gammas, positrons, neutrons. Commonly, protons, deuterions. Oh, these are all, I forgot to fix this. All of these are off by a word. This is protons. This is deuterions. This is tritons. These are encountered in nuclear reactions. A minute. Let me fix that right now. If I can. Oh, no, I can't edit this. That's why I didn't fix it. So here's an example of the proton bombardment of lithium-7. You hit lithium-7 with a proton, you get something and it spits out a neutron. The sum of the masses on the left has to be 8. So whatever we make has to have a mass of 8. The sum of the atomic numbers on the left is 4. So this is going to be the sum of the atomic numbers on the right must also be 4. A neutron has an atomic number of 0. So we must have 4 protons in whatever we make. That is beryllium. The missing particle has a mass of 7 and an atomic number of 4. So the completed equation is we get beryllium-7 and a neutron. And here this is the deuteron bombardment of aluminum-27. We shoot deuterium and deuteron into aluminum-27. That creates something new and spits out a helium nucleus. So the sum of the masses on the left is 29. So the sum of the masses on the right must also be 29. So the missing particle has a mass of 25. And the sum of the atomic numbers on the left is 14. So the sum of the atomic numbers on the right must also equal 14. So this will be 11 as the atomic number. It'll be 12 as the atomic number. So the missing particle must have an atomic number of 12. So it is a mass number of 25, atomic number of 12. This is magnesium 12. And Rutherford's discovery of the transmutation of nitrogen 14 into oxygen 17 was actually an accident, but the implications were enormous. One element could be changed into another, completely different element. And the age-old dream of alchemists had become true. It was actually now possible to make gold. So here's an example of a simple reaction that makes gold, where you hit mercury with helium, and it turns into gold 197. And mercury with hydrogen turns into gold 197 and helium nucleus. This process is very expensive. It's more than $1 million per ounce. And the one for leaded to gold is even more expensive. And neutrons produced in nuclear reactions can be used to induce other nuclear reactions, so you can get a chain reaction. And since neutrons don't have an electrical charge, they're particularly efficient in penetrating the nucleus and inducing a reaction. And without an electrical charge, neutrons are not influenced by positive and negative atomic charges. So it's very easy for them to go out and trigger something else, which is why it is the bombardment by neutrons that is used to make it the big boom. The chain reaction for nuclear fission that makes atomic bombs work is the emission of neutrons. And you know what? We will finish this next time and continue on with something else. But yeah, that's where I'll stop for today. So,